Hey, AP Statistics. So continuing on with 6.3, the binomial distribution. So we're going to look at the shape, center, and variability or spread of the binomial distribution. So this table shows that same example where we had 5 trials, a 25% chance of success. And these are all the different binomial probabilities. We could go through and done a binomial PDF to calculate all of those probabilities. So what is the shape, center and spread of that distribution? And so the distribution, if we graph it, we can see that it is skewed to the right in this case. And yeah, we can kind of estimate the center off of that. We could do our calculation for the mean and standard deviation using outcomes, list 1, list 2, and calculate all those. But that's what we're going with here. We got 25% chance of success. So yeah, you can kind of think about out of 5, 25% of that, would be maybe a little over 1. That's obviously you're going to have just 1 or 2, but I guess that kind of makes sense. So what if we change that probability up? And what if we go to a probability of 51%? So now we see that this same number of trials, but if we move it up to a 51% chance of success, now it's kind of symmetric. It's not smushed up there against 0 anymore. And if we dial that up even higher to 80% success, now we're kind of smushed up against the top end, and so we're skewed to the left. So we're bounded by those possibilities. We can never go below 0 or above 50%. In between, we're kind of symmetric over that range, but if we kind of smush in too high of a probability, we end up with a kind of a left skew because we're smushed up against the top bound. If we go too low of a probability, we're going to end up having a right skew because we're smushed up against that lower bound. All right, and so we'll see that, yeah, if we stay far enough away from those, we have a fairly symmetric distribution, and even actually gets a little better than that too. All right, so then the mean and standard deviation of a binomial distribution, and so the expected value of that random variable is n times p, so the number of trials times the probability of success. I actually just did that on the other slide, where we had 5 trials with a 25% chance of success. If you multiply 5 times 25%, that's your expected value, that's your average. So it's a nice, simple calculation, number of trials times the probability of success. If I'm flipping a coin 50 times, multiply it by 0.5, I'm going to expect 25 successes. That's going to be my average of that distribution. Doesn't mean that's what's going to happen, just this long run. If I keep flipping 50 times, flip another 50 times, flip another 50 times, the long run, I expect that average to average out to 25 successes. And then the standard deviation is a little different, but you do get this formula. The standard deviation, you take the square root of the number of trials times the probability of success times the probability of failure, 1 minus p. And that actually gives us our standard deviation. So actually a pretty simple formula for that. And I could go into some proof of this, but I'm gonna leave that aside for now and just kind of accept it as that is a given formula that can help you calculate the standard deviation of a binomial random variable. Now this only works for binomial distributions. So those only mean the standard deviation of a binomial distribution. So assume that each of 21 students in Mr. Hogarth's AP Statistics class who did the bottled water versus tap water activity was just guessing. And so there was, yeah, they're trying to figure out whether it's bottled water versus tap water. And so there was a 1/3 chance of each student identifying the cup containing bottled water correctly. Let x equal the number of students who make correct identification. At right is the histogram of the probability distribution of x. So x is random variable. We had 21 students. They had a 1/3 chance of success identifying the which of the 3 bottles was bottled water. And so if this is the, if that's that distribution, we see here that, the kind of the shape of it, it looks like it's kind of symmetric, maybe a super slight right skew, but yeah, this looks pretty good in terms of a symmetric distribution. But where is it centered? What is the spread is what we're going to look at next. So calculate, interpret the mean. So we had 21 trials. We had a 1/3 chance of success. So if we multiply those two, that'll give us the mean, 7. N times p. So to interpret that, if all the students in Mr. Hogarth's class were just guessing and repeated the activity many times, the average number of the students who would guess correctly would be about 7. Calculating the standard deviation, using that formula, square root of n times p times 1 minus p. So in this one, it's square root of n, which is 21, times p, when 1/3, 1 minus p is 2/3. Let's calculate that all up. And that's the typical deviation. So if all the students in Mr. Hogarth's class were just guessing and repeated the activity many times, the number of students who guessed correctly would typically vary by about 2.16 from that mean. All right, so a little weird feature comes up with here is the idea of sampling. When we're sampling, we're going to wonder if we can treat that as a binomial distribution in a binomial setting. So in almost all real-world sampling, such as taking a simple random sample from a population, we're doing it without replacement. We're not replacing individuals. So that violates a condition for being a binomial setting. So sampling without replacement leads to a violation of the independent condition in the binomial setting. Technically, as I remove individuals, say I'm interested in individuals with type O blood from our population. As I start to sample and remove individuals, technically, if I take one individual out of the population, now those individuals remaining, a slightly different proportion of them actually have type O blood. If I've removed somebody with type O, then it's a little lower. If I remove somebody that didn't, it's actually a little bit higher. But that change can be very insignificant. And so, but when the population is much larger than the sample, the number of successes in a simple random sample of size n is an approximately binomial distribution. Basically, it's approximately independent, right? If I randomly select people from a population, I want to know what's the probability to get a boy or a girl. Technically, if I remove one boy from a population, now the probability of getting a boy has changed. But it's changed so insignificantly that we treat it like it is independent. And we just kind of go ahead. And so, for instance, we could treat that as a binomial setting. So when we are taking a sample of size n from a population of size capital N, we can use the binomial distribution to model the count of successes in the sample as long as our sample size is less than 1/10 of the population. So we can set that up. Or if we say the population is 10 times the sample size, you can say it either way. The sample needs to be less than 1/10 of the population, or the population needs to be 10 times the sample size. So we call that the 10% condition. And we'll check that a lot whenever we're talking about sampling. So, for example, in a survey of 500 US teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that exactly 12% of teens aged 14 to 18 have debit cards. So this chapter, we're doing a thing where we're like assuming we know these things. Eventually we'll get to the point where we realize we don't actually ever know exactly these percentages, but we're going to work with these assumptions for a little while. So let x equal the number of teams in a random sample of size 500 who have a debit card. So in this case, explain why x can be modeled by a binomial distribution even though the sample was selected without replacement. So this is because that our population, US teenagers, all US teenagers, is really, really large. And this is definitely less than 10% of that. So less than 10% of all US teenagers were selected. The binomial distribution, so use the binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. We're definitely going to want to use our calculator for this because we're going 50 or fewer, less than or equal to. So we want a probability of 50 plus a probability of 49 plus a probability of 48 and so on and so forth. We are not going to do that by hand. So we're going to do binom CDF to do this calculation. Our number of trials is 500. That's our number of individuals. Our probability of success is 12%. We're taking that as fact. So this would be that calculation. Binomial probability with n is 500, p is 0.12. Notice that they're explaining all this. And then the probability x is less than or equal to 50. Here's how they would type that in. The number of trials is 500, p is 0.12, and we're interested in 50, and then since it's CDF or fewer. And so apparently there's a 9% chance. All right, the last bit of this section I'm going to breeze through real quick. Basically, we don't have to know this now, so I'm not going to require it yet. But that binomial distribution, you may have noticed that it gets kind of close to a normal approximation. So this is not required now, but for a certain sample size, if we have 10 trials and an 8% chance of 0.8% chance of success, 80%. Sorry, got that right there eventually. 80% chance of success, 0.8. That is definitely not a normal distribution. In fact, it's skewed left. It's peaked up there. But if we get a bunch of trials, eventually we end up with a very close to this normal distribution. And so that's a really neat feature that we can use on down the road, is that this distribution becomes approximately normal as long as we have enough trials, enough counts, enough space for it. And so this is actually the condition. We call it the large counts condition, that distribution of x is approximately normal as long as these two conditions are met. That the number of trials times the probability of success is at least 10. So that's actually n times p is your average, your mean. Your mean needs to be at least 10, so we have to expect at least 10 successes and have room for kind of a curvature of below that. And then this is actually your expected number of failures, n times 1 minus p, and then that also has to be at least 10. And so that makes sure you have kind of enough room to have that nice kind of curve shape to it. So we'll check this condition. We call this the large counts condition in the future to see if we are approximately normal. We're not going to focus on it with binomial, but it's going to come back when we deal with proportions in future chapters.